Hello everyone. Today we are going to solve some numericals which is related to earth pressure theories. So these numericals are very important to understand how the problems are being carried out or how to find out the earth pressure for various kind of soil and various type of soil conditions. So let us go through the first problem. What has been given in the problem? Compute the intensities of active and passive earth pressure at a depth of 8 meters in dry, cohesionless sand with an angle of internal friction of 30 degree and unit weight of 18 kilonewton per meter cube. What will be the intensities of active and passive earth pressure if the water level rises to the ground level? Take the saturated unit weight of sand as 22 kilonewton per meter cube. So we have two type of soil. The first is the dry soil and second is the submerged soil when the soil is under water table. So let us find out the value of active and passive earth pressure for the dry soil. So as we all know that the value of the active earth pressure coefficient Ka is given by 1 minus sin phi by 1 plus sin phi, and coefficient of passive earth pressure is given by Kp equals to 1 plus sin phi by 1 minus sin phi. So let us substitute the value of phi as 30 degree, and after replacement of this value of 30 degree we are obtaining Ka as 1 by 3 and Kp as 3. So let us find out the value of the active earth pressure, that is Pa equals to Ka into gamma into H, where Ka is the active earth pressure coefficient, gamma is the unit weight of the soil and H is the height of the retaining wall. Hence Ka, substituting Ka as 1 by 3, the value of gamma is given as 18 kilonewton per meter cube and the value of the total height of the retaining wall has been given as 8 meter. Hence we are obtaining the value of active earth pressure as 48 kilonewton per meter square. And what is the value of the passive earth pressure? The value of passive earth pressure is given as Kp into gamma into H. So substituting this value 3 into 18 into 8, it is given as 432 kilonewton per meter square. So this is the value of active earth pressure and this is the value of the passive earth pressure. So for the submerged backfill, what will happen? So for the submerged backfill, we know the value of the submerged unit weight of the soil is given by saturated unit weight minus unit weight of water. So the saturated unit weight of the soil is given as 22 kilonewton per meter cube, and 22 minus the unit weight of water is considered as 9.81 kilonewton per meter cube. Hence the value of gamma submerged is given as 12.19 kilonewton per meter cube. So when the submerged backfill is present, as we have already gone through the earth pressure chapter, that the active earth pressure coefficient and the value of the active earth pressure intensity is given by, in case of submerged soil, is given by Ka into gamma sub into H plus gamma W into H. So here substituting all these value, we are getting approximate value of the coefficient of active earth pressure as 111 kilonewton per meter square and coefficient of passive earth pressure as 371 kilonewton per meter square. So this is the value of the active and passive earth pressure for dry soil and submerged soil. So let us shift to the second problem. What is there in the second problem? A retaining wall 4 meter high has a smooth vertical back. The back has a horizontal surface in level with the top of the wall. There is uniformly distributed surcharge load of 36 kilonewton per meter square intensity over the backfill. The unit weight of the backfill is 18 kilonewton per meter cube. Its angle of shearing resistance is 30 degree and cohesion is 0. Determine the magnitude and the point of application of the active pressure per meter length of the wall. So we have to find out the intensity of active earth pressure per meter length of the wall. That means on the total wall. So let us find out the coefficient of active earth pressure. So how it can be find out? K equals to 1 minus sin phi by 1 plus sin phi. Putting the value of phi as 30 degree, we can obtain K equals to 1 by 3. So what will be the value of the earth pressure in case of surcharge? We all know that for the value of surcharge, as it is uniformly distributed towards the wall surface, it is given as Ka into Q. So the value of the surcharge load will be equals to 1 by 3 into 36, that is 12 kilonewton per meter square. This is the intensity of pressure due to the surcharge load. So let us come back to the intensity of active earth pressure. The intensity of active earth pressure is given by Ka into gamma h. Substituting the value of Ka, gamma is given as 18 kilonewton per meter cube and height of the wall is 4 meter. Hence we are obtaining the value of earth pressure as active earth pressure as 24 kilonewton per meter square. So adding these two values, we are getting the total intensity of pressure at the bottom of the wall, that is 12 plus 24 equals to 36 kilonewton per meter square. In the second figure, you can easily see the value of the intensity of the pressure at the top of the wall and at the bottom of the wall. So there are two pressure distribution diagrams for P1 and P2. So the resultant pressure, if we find out the resultant pressure, that is capital P1, this is given by 12 into 4, that is for the rectangular portion, which is the surcharge portion. So if we need to find out the resultant pressure, that is 12 kilonewton per meter square pressure is acting on 4 meter wall, so that will be the intensity of the pressure will be 48 kilonewton per meter. But where will be the pressure acting, as this is a rectangular figure or the rectangular intensity diagram, so the center of the pressure will be acting at the half from the base, so that is at 2 meter distance from the base of the wall. So hence the pressure is acting at 4 by 2, that is 2 meter from the base of the wall. So the resultant pressure or the resultant total pressure for P2 is given by half of P2 into H, that is half of 24 into 4, that is 48 kilonewton per meter, and which is acting at 1/3 of the distance, that is 1/3 of 4, that is 1.33 meter from the base. So for the rectangular part, it is acting at a distance of h by 2 from the bottom, and for the triangular part, the intensity of pressure is acting at 1/3 from the bottom. As we know, for the triangle, the centroid lies on from 1/3 from the base of the wall. Hence the total intensity is given by 48 plus 48, that is 96 kilonewton per meter length of the wall. Hence the resultant P act as a distance of z bar above the base. So if we take the moment about the base, we can obtain 48 multiplied by 2 plus 48 multiplied by 4/3 divided by 96. Hence we can obtain the resultant pressure for surcharge as well as active earth pressure is given at a distance of 1.67 meter from the base of the wall. So here the Z value is given as 1.67 meter. At the bottom, the total intensity is 36 kilonewton per meter square, and at the top it is given as 12 kilonewton per meter square. So this is the second numerical problem. Let us go to the third numerical problem. What is been given in the third numerical problem? In example 20.3, if the water table rises behind the wall to an elevation 1.5 meter below the top, determine the total active pressure and its point of application. Take the submerged weight of the sand as 12 kilonewton per meter cube. Assume that there is no change in the angle of shearing resistance due to the submersions. So this is the continuation of the second problem, that is, if the water table rises, because here in the problem we have not recorded or we have not considered the water table. But in the second problem, what we need to do, we have to consider the water table. That is, if the water table rises at an elevation of 1.5 below the top of the wall and the submerged weight of the sand is considered as 12 kilonewton per meter cube. So what will be the change in the active earth pressure? And we have to assume that the angle of shearing resistance will remain constant for both the cases. So let us solve the problem. So we have to divide the problem into various parts. The first part, or the P1, will be the lateral pressure intensity due to the surcharge. It will be uniform. P2 will be the lateral pressure intensity due to the dry soil, that is at the top soil. P4 will be lateral pressure intensity due to the submerged soil, that is the soil which is submerged under water. And P5 will be the lateral pressure intensity due to the water. So these are the total pressure intensity that is acting on this problem. So let us calculate the value of P1. As we all know, P1 can be calculated as Ka into Q for the Surcharge weight, that is one third of 36 equal to 12 kilonewton per meter square. In case of P2, the value of the active earth pressure is given as Ka into gamma into H1, that is top 1.5 meter. So one third of 18 into 1.5, that is 9 kilonewton per meter square. For the fourth, for P4, submerged unit weight of the soil, so Ka into gamma sub into H2, that is one third of 12 into 2.5, it is 10 kilonewton per meter square. And for the fifth part, gamma W into H2, that is pressure due to the water, 9.81 into 2.5, that is 24.53 kilonewton per meter square. In this figure, it shows the pressure distribution diagram with the resultant pressure of P1, P2, P3, P4 and P5. So here the distribution diagram is already being provided. So let us calculate the capital P1. So capital P1 of the total pressure is given as P1 into H, small p1 into H, that is 12 into 4, 40 kilonewton per meter. So where this pressure is acting, as we can see in the diagram, that this is a rectangle. So the pressure is acting from half of the base, that is half of P2 into H1, that is half of 9 into 1.5, that is 6.75 kilonewton per meter. Again, the rest of the pressure where they are acting at, for the second case, it is acting at total, the distance will be 2.5 from where the water table is being considered, and the topmost portion is 1.5. Hence for the topmost triangle, that is P2, here the one third from the base of the wall, that is one third of 1.5 plus 2.5, that is the bottom distance, has to be considered. So in case of P3 can be seen, it is also a rectangle which can be find out by multiplying P2 with H2, which is acting at the distance of 2.5 by 2, that is 1.25 meters from the base of the wall. For P4, it is a triangle, hence we can find the pressure intensity as half of P4 into H2, that is half of 10 into 2.5, that is 12.5 meter, acting at a distance of one third of 2.5 meter, that is 0.833 meter from the base. And so for P5 is considered, it is also a triangle where half of P5 into H2, that is half of 24.53 into 2.5, which gives 30.66 meter, acting at a distance again 2.5 by 2, that is 0.833 meter from the base. Hence the total intensity of earth pressure is given as P1 plus P2 plus P3 plus P4 plus P5. Hence by adding all the sums, we are getting the value of 120.41 kilonewton per meter. So if we consider the point of application of the P above the base, then we have to find out the value, that is 48 into 2 plus 6.75 into 3 plus 22.5 into 1.25 plus 12.5 into 0.833 plus 30.66 plus 0.833, and calculating all this value, we can get the value of Z bar as 1.5 meter. That is the total pressure intensity of 120.41 kilonewton per meter is acting at a distance of 1.5 meter below the base of the wall. So this is the next problem. Let us shift to the another problem. So this problem consists of an unsupported excavation is to be made in a clay layer. So the previous soil was mainly cohesionless soil, and this soil is made up of a clay layer. Here gamma is given as 18 kilonewton per meter cube, value of cohesion is given as 30 kilonewton per meter square, and the value of phi is given as angle of shearing resistance is given as 10 degree. That means there is a value of C as well as there is a value of phi. We have to calculate the depth of the tension crack. Next, calculate the maximum possible unsupported depth and the active earth pressure distribution diagram. So let us find out the active earth pressure coefficient first. So as we all know, K equals to 1 minus sin phi by 1 plus sin phi. Substituting the value of phi as 10 degree, we can obtain the value of Ka as 0.704, which is also equals to cot square alpha. Next, what is the value of coefficient of active earth pressure for cohesive soil? It is given as Ka into gamma z minus 2c into root over of Ka. So here, putting all these values, we can obtain the value of Pa as 12.672 Z minus 50.343. For the top surface, we know Z or the depth of the retaining wall will be 0. Hence, the active earth pressure at the top of the wall is given as minus 50.343 kilonewton per meter square. That is, the minus sign indicates the soil is in tension, not in compression. So where will be the pressure intensity become 0? So Pa will be 0 at Z equals to 50.343 divided by 12.672, that is 3.973 meter. Hence the depth of the tension crack, or where the active earth pressure intensity will be 0, is given as 3.973 meter. So what will be the maximum possible depth of the unsupported vertical cut? So twice of the tension crack, that is 2 into 3.973, that is 7.946 will be the maximum possible unsupported length of the vertical cut. And what will be the pressure at the bottom? The pressure at the bottom is given as 12.672 multiplied by Z, that is 7.946, minus of 50.343, that is equal to 50.343 kilonewton per meter square. Hence the active earth pressure diagram before the occurrence of the crack is given in figure number B, and after the formation of the tension crack, the pressure diagram is shown in the figure C. So this is the value of the earth pressure in case of a C5 soil. Let us go to another problem which is also of cohesive soil. A retaining wall with soft saturated clay backfill is 7 meter high. For the undrained condition, that is, we all know for undrained condition phi equals to 0. For the backfill, we have to determine the maximum depth of the tension crack, the active force before the tensile crack occurs, the active force after the occurrence of the tensile crack. Here the value of gamma is given as 16 kilonewton per meter cube. Value of the undrained cohesion is given as 17 kilonewton per meter square. So we have to find out these are the values. So first of all, let us find out the coefficient of active earth pressure. As we know, as the value of phi is 0, so value of Ka will be equal to 1, substituting phi equals to 0. So hence the value of the tension crack is given as 2c by gamma into root over of Ka, that is 2 into 17 by 16 is given by 2.125 meter. So before the crack develop, so what will be the value of the active earth pressure? Pa is given by half of gamma into h square cot square alpha minus 2ch into cot alpha. So substituting all the values, we are obtaining the value of active earth pressure as 154 kilonewton per meter. So when the crack develops, so the soil becomes inactive. Hence, in this case, the value of the active earth pressure is given as half of Ka into gamma into h minus z naught square, where z naught is the depth of the tension crack. So substituting all this value, we can get the value of the development of tension crack. Intensity of active earth pressure is given as 190.125 kilonewton per meter. So this can also be solved from any alternate equation, as we already know that the total intensity of active earth pressure for cohesive soil is given as half of gamma into h square cot square alpha minus 2ch cot alpha plus 2c square by gamma. So substituting all this value, we can obtain the intensity of active earth pressure as 190.125 kilonewton per meter. So these are the numerical problem which are of very important from active earth pressure chapter. Thank you.